Recording in progress.
Okay, so it says a total charge of 9 m is milli, okay, the prefix milli. So 9 millicoulombs passes through a cross-sectional area of nichrome wire in 3.5 seconds. In part A, they're asking you to find part A, it says what is the current in the wire. Part B, how many electrons pass through the cross-sectional area, but now in 10 seconds. And then if the number of charges that pass through the cross-sectional area during the given time interval doubles, what is the resultant current? Okay, so for current, you know that we need to highlight the givens. They're giving me a charge of 9 millicoulombs, they're giving me a time of 9 seconds, and in part A, they're asking me to find the current in the wires. So for part A, I will write my givens, okay? I have the charge is 9 millicoulombs, okay? This is the same as having 9 times 10 to the negative third power coulombs. Remember, the prefix milli is times 10 to the negative third power. Remember, the prefixes are in the page 12 from your textbook. Now, they're giving you a time interval of 3.5 seconds, and they're asking you to find... Ay, Dios, no tengo batería. Wait, wait. Ow. Wait. Okay, they're giving you a time of 3.5 seconds, and it says that you need to find a current. Okay, so the current is unknown. Okay, so according to the formulas that I gave you, current is equal to charge divided by the time interval. So you say, this is the main equation, current is equal to Q divided by delta T. All we need to do here is to plug in the givens. You know that the charge is equal to 9 times 10 to the negative third power coulombs, and the time is 3.5 seconds. How much is this current?
2.57 times 10 to the negative third power.
2.57 times 10 to the negative third power amperes. That is the first answer that we need. Okay? So, in this wire, the current that is being provided for this wire is 2.57 times 10 to the negative third power. Now, wait a second that this thing is not updating. Okay, now that is the first part. We already finished with the first part. Then it says, how many electrons pass through the cross-sectional area in 10 seconds? Now, as you can see, they're asking you for electrons, but they are telling you a different time now. Okay, they are telling you a different time. So what happens in part B? For part B, they are giving you a different time. They are giving you... Esta cosa no actualiza. Wait a second. Now it is updating finally. Okay, so the givens for part B, you have a time of 10 seconds. So what happened with this time? If you know this time, you need to find a new Q, okay? Because this charge that was provided here in the beginning, in part A, they gave you a Q, okay? So, what is going to happen? Now that you have more time, you're going to have a different charge, okay? Now, all the charges that are going to pass through the wire in 10 seconds, it has to be more, which means that you need to get a new Q, okay? So, with this time, you're going to get a new Q, but the current remains the same. You know what is the current in the wire. We got it in the step before, okay? So, 2.57 times 10 to the negative third power amperes takes the place of a new given, and we need to find the new Q, okay? So I apply the formula to find Q, and I say Q is equal to current times delta T. I plug in the givens. My current, that is 2.57 times 10 to the negative third power amperes, multiplying 10 seconds. Remember that amperes is a compound unit, okay? That is coulomb over seconds. So now that you're multiplying all these units, you should be able to get rid of seconds, okay? So the remaining unit will be just coulombs. So the new Q gives me 2.57 times 10 to the negative second power coulombs. This is the new charge, okay? This is the new charge. Now, well, but this is not what the problem in part B is asking you. Okay, so now you have to find it. You have the new Q, and you need to find number of electrons. That's the purpose of part B. You need to find the number of electrons. Okay, so the number of electrons is the real unknown here. Now to do that, in the second step, what we're gonna be doing is, remember what we used to do before when we used to work with current, okay? And they gave you number of electrons, you can get a time. But now they are giving you the time, okay? The time is now 10 seconds. You have already the current obtained from the step before. From all this, you can get Q. Now that you have Q, you can get the number of electrons. How can you get the number of electrons? By using the conversion factor, okay? You know that in one electron you have 1.6 times 10 to the negative 19 power coulombs. So with this, we are going to do the procedure, okay? So in this case, knowing Q, we are going to get the number of electrons. So we start by using Q. You have 2.57 times 10 to the negative second power coulombs times the conversion factor. The conversion factor says that in one electron you have a charge of 1.6 times 10 to the negative 19 power coulombs. This allows you to get rid of coulombs, and in the end will give you number of electrons. I got, let's see if you got the same as me. I got 1.61 times 10 to the 17 power electrons. This is the answer I'm looking for. So, I already solved the part B. But now in part C it says, if the number of charges that pass through the cross-sectional area doubles, okay, that is important because it's telling you that if the number of charges during the given time interval doubles, what is the resultant current? Okay, so we're going to consider the same first interval, but we're going to increase the charge. We're going to double the charge. So we say in part C, it says the, the same time interval, so the time interval is 3.5 seconds, okay? But it says if the number of charges doubles. So this is my charge. My charge is 9 millicoulombs, but it says that it doubles. That means that it's going to be multiplied times 2. In other words, this is 18 millicoulombs. Replace the prefix milli. You're not seeing anything, sorry.
Me, so that thing is to be 10 seconds.
Can you repeat, please?
I think it should be 10 seconds.
Well, if you do it with 10 seconds, it should give you the same answer, but you have to use a different charge. But I did it with this time. But, but let's see if we can do it later with the time of 10 seconds, okay? If the time is 10 seconds, the charge is different. Remember that we got a different charge for the one of 10 seconds. The charge for 10 seconds is 2.57 times 10 to the negative second coulomb. Okay, so we can do it in the two ways. I'm not completely sure if it would work, but it should work. Okay, it should work the same way. Okay, so it says that if in the time interval, well, if in the time interval the charge doubles, so that means that this charge is gonna be multiplied times 2. Okay, this gives me the new charge. I forgot what is the problem is asking me. What is the resulting current? What is the resultant current? Okay, and here is this is 18 times 10 to the negative third coulomb. Okay, so I'm gonna look for the current. Current is Q divided by time. So this will be 18 times 10 to the negative third power coulombs divided by 3.5 seconds. So the current here gives me 0.0051 amperes. If I do it in the other way, I'm going to apply the same formula. Current equals Q divided by delta T equals 0.051 C divided by the time, that is 10 seconds.
Yes, it's the same answer.
So as I told you, choose one of the, okay, choose one pair of givens and work with them. So you can either do it with 10 or 3.5 seconds. Just remember to use the charge that it corresponds. So remember, for the first part, they are giving you this charge for this specific time, 9 millicoulombs for 3.5 seconds. But in this other part, we got a new Q, we got a new charge because we had more time. So you can use the two values. In the end, the current, as you can see, it remains constant. Do you have a doubt about this problem? It was a little bit long, but you know the formulas are quite simple. Okay. Now in the exercise 6, this is about resistance. Okay. From page 601, if I'm not mistaken. Okay, here it says current in a certain resistor is 0.50 amperes when it is connected to a potential difference of 110 volts. If the current in this same resistor, what is the current in this same resistor if operational potential difference is 90 volts and the operational potential difference is 130 volts? Okay, so we have two parts in this problem. The givens are, for part A, they are giving you a resistor, okay, which has this current, 0.5 amperes, a potential difference 110 volts, and they're asking me to find the current in part A. They're asking me to find the current is unknown, but now the potential difference changes to 90 volts, okay, and in part B it says that I need to find the current and the potential difference is 130 volts. Okay, so what can we do with these two givens? According to the formulas that I gave you, I can get resistance. Now, we have the Ohm's law. Remember the triangle that I gave you? We can use it to get resistance. Resistance is potential difference divided by current. Okay, so we say resistance is equal to potential difference divided by the current. All we need to do is substitution of the data. Okay, delta V is 110 volts and the current is 0.5 amperes. Okay, this gives me a resistance of 220, and here we have ohms. The problem is not asking me to find the resistance, but I need it. Okay, the reason is we are talking about a certain resistor. This is my object. Okay, this is my object. If I have to do a sketch about what I have in this problem, it's going to be, I have my source of potential difference, that is 110 volts. Only I want to do this because I want to show you the difference. Okay, so I have my source of potential difference right here, that is 110 volts. Now what I have here is a resistor. Okay, so this resistor, I'm not changing it. Okay, I'm just saying that for the first situation, when it is connected to 110 volts, my current is 0.5 amperes. With this, I know that I can get my resistor, which is 220, sorry, that is 220 ohms. This is my resistor. Okay, this is my resistor. Now, I'm going in part A, I'm changing the source of potential difference. Is not 110 anymore. Now it's just 90 volts. Okay, if I change my voltage, I'm not changing my resistance. My resistor is going to remain the same. What is going to change is the current. Okay, so I'm going to calculate the new current. To do that, I'm going to be using the same equation but isolated for current. Current is equal to potential difference divided by the resistance. Now I know the resistance. The resistance given for this problem, it is implicit, is 220 ohms. Okay, so all I do, okay, sorry. So now all I do, I just need to plug in the givens. I'm gonna have a different current. 90 divided by 220 gives me 0.41 amperes. In other words, my current is going to change because it depends directly on the potential difference. Okay, so when the potential difference is 90 volts, my current is 0.41 amperes. But now the situation changes. Now my voltage is not 90 anymore. Now is 130 volts. Okay, the resistor, I'm not gonna change it, but this new system is going to provide me of new current. My current is equal to potential difference divided by the resistance, and this gives me the current to be 130 volts divided by 220 ohms. My new current is equal to 0.59 amperes. In other words, in this sketch on this circuit, my new current, when I have this arrangement of 130 volts and one resistor of 220 ohms, the current is going to be 0.59 amperes. That's what it means. That's why these are the two answers that the problem asks you to find, okay? But to do that, before you had to get the resistance. Now today, guys, I'm planning to explain, or at least to start explaining, this topic about electric power. First, we need to talk about the sources and the type of current. We have sources of current like batteries or generators. Batteries are everything that is rechargeable, like your phone, for example. It includes a rechargeable battery. So when you're running out of battery, you just plug it into any outlet over there, and your phone after 1 hour is going to be probably completely charged. Now, what in a battery, the energy is batteries transform chemical energy into electrical energy. The reason is because inside a battery we have acids. Those acids are in constant in constant reaction, and that reaction is going to release energy, and that energy is the one that is being transformed into the electrical energy. That's how a battery works. But then we have generators. Generators are more complex or less complex. It depends on your point of view, I guess. But generators are at least more expensive, because you can go to La Pulperia and a battery will cost around 20 lempiras, but a generator is going to cost 20,000 lempiras. So there's a big difference. With a battery, you can turn on a flashlight, but with a generator, you can turn on everything that you have in your house. So generators are amazing. Generators in they work different from batteries, because generators, what they do is that they convert mechanical energy into the electrical energy. We have another kind of power plants like hydroelectric power plants, another source of current, but they transform potential energy into electrical energy. So we have different kinds of suppliers of current. Which one to use depends on what you have, in of what you required. Now, we have types of current. There are two types of current: AC, DC. Yeah, like the rock band. Okay. Uh, AC refers to alternate current, and DC refers to direct current. Okay. Now, in this chart, you can notice the two difference. Well, the main difference between them. In the red current, you notice, sorry, in the red current, you notice that the current remains constant, because this line doesn't go up and down. Okay, you can see it's constant. It keeps the same value throughout all time. Okay, imagine that this is 1 hour. During this 1 hour, it's using this amount of current. Imagine this is 2 amperes. It's going to keep 2 amperes the full time. But then in alternate current, the current is gonna be changing. You can see it's coming from 0 to 0, -2 is changing. Okay, now this is the main difference between direct and alternate current. Current is constant in direct current, but is not constant with alternate current. And then is when electric power comes in. Electric power is the rate at which charges are able to do work. I explained you power last year. I told you that by definition, power is the rate at which you can do work in a certain time interval. But here are the individual works that every little charge is doing. You add all those works, you divide it by the time they're working, and you will have the electric power. Recall that the SI unit is the watt. Okay, and 1 watt is equivalent to 1 joule per second. These are the possible isolations and these are the word problems. I want you to write down these word problems in your notebook. I don't have time to explain you, not even one exercise because I